So today we'll start with electrophilic substitution reaction of phenol. So first of all we will see, if we say phenol, the phenol is ortho and para directing in nature. Now the substitutions that are attached to the benzene, which are directing in nature the incoming group. Okay, so this phenol is ortho and para directing. So any incoming electrophile that will be attached in ortho and para position. If you see why it is ortho para directing, due to presence of this lone pair of electron and oxygen, this lone pair transfers here and there is formation of double bond. There is formation of OH plus okay. Then further the electron transfer from here to here, the negative charge will appear here, OH plus, and so there will be 5 resonating structure showing that phenol is ortho and para directing in nature. That means the negative charge or the electron density is higher at ortho and para positions. Okay. So if there will be any incoming electrophile, that will be attached to the benzene ring at ortho and para positions. Okay. So we will see the direct electrophilic substitution. We consider an electrophile as E plus. So first of all, there is phenol ring OH. Okay, this phenol ring is ortho para directing, we have seen earlier. So first of all, there will be delocalization of electron. Okay, next double bonds, delocalization double bond here, and okay, let me move this side. Let's consider phenol. Alright, first of all, there will be the electron. Let us consider that if it is bonded to the ortho carbon, with formation of OH plus, and this will be H, this will be electron plus, and in the next step there will be removal of this hydrogen and formation of OH and the electrophile attached to the ortho position. The driving force of this reaction is formation of more stable aromatic compound. If you see, this one is non-aromatic, if you lose one H plus and there will be formation of aromatic. This is the driving force for the formation of the removal of H plus and formation of phenol. Okay, and now one by one we will see different electrophilic substitution. First we will see with bromination. Of phenol. Okay. If we see, if we carry out the bromination of phenol in presence of in aqueous solution, there will be formation of 2,4,6 the formation of 2,4,6 tribromo phenol. This is tri substituted. Okay, but if we carry out this reaction in presence of non-polar solvents like CCl4 or CH2, so this will be monosubstituted. So there will be formation of either orthobromophenol or formation of parabromophenol. This is because when you do this reaction in aqueous medium, so in aqueous solution, phenol is little bit acidic in nature. So in aqueous solution, this phenol will undergo dissociation and formation of phenoxide ion plus H plus. Due to this formation of phenoxide ion, the electrons are more available. Hence, due to high electron density, this will be tri-substituted. Okay. But instead, we see in inert solvents like carbon tetrachloride or CH2, this will not be tri-substituted, this will be monosubstituted at ortho or para positions. Okay, if you consider there is substitution at para position, let us consider phenol. If we add these two, Br2 in presence of CCl4 or CH2. Okay, first of all, the electrophile will be Br plus. Okay. Next, we consider direct electrophile Br plus. Okay, first there will be movement of electron from here to here, and from here, so there will be attack of this negative charge. Now from here, this will direct attack to bromine, and there will be formation of OH plus double bond bromine hydrogen, and in the next step, then we remember of this H plus, this bond will transfer here, this bond will transfer here, and there will be formation of parabromophenol. Okay. This is the electrophilic substitution or electrophilic bromination of direct bromination of phenol. Okay. The parabromophenol will be the major product. Okay. Next we will see nitration of phenol. For nitration of phenol, we react phenol with dilute HNO3 or nitric acid to form orthosubstituted plus parasubstituted orthonitrophenol and paranitrophenol. But instead, if we use, instead of direct HNO3, if we use concentrated HNO3, there will be formation of a less amount with a low yield formation of picric acid or 2,4,6 trinitrophenol, which is also known as picric acid. Okay. The reason is same as we have in the, as the concentrated HNO3 is highly reactive, so it will be tri-substituted. Okay. The next is sulfonation. Sulfonation of phenol. Sulfonation is also one type of electrophilic substitution. So first of all, there will be generation of electrophile. If we consider the structure of sulfuric acid, this will be OH, as this is acid, so there will be H plus in the solution. The first step there will be protonation, OH2 plus and single bond OH. The next step there will be removal of water, formation of S double bond O plus double bond O OH. So in the next step, transfer of electron minus of H plus and formation of SO3. So here this SO3 has vacant orbital, so this acts as electrophile. In the sulfonation, the SO3 acts as electrophile. Okay, in the next step, if we consider the ortho substitution, okay. Phenol take with SO3, there is vacant orbital, so electron transfer from here, formation of double bond, transfer from here, so formation of double bond OH plus H SO3 minus. As the transfer of electron from here to here, this accepts electron becomes SO3 minus. The next step, removal of H plus, the driving force is aromatization. SO3 minus, and it takes up the H plus and formation of SO3H. Okay. So this is the sulfonation of benzene. Okay. Alkylation. If we are reacting with phenol, there is one phenol, there is one alkyl halide, and with that there is presence of one Lewis acid, such as anhydrous LCl3, or we can also take anhydrous FeCl3. If we are doing with instead of CH3Cl, if we are reacting with CH3Br, we can react this in presence of Lewis acid like FeBr3. Okay, these all are Lewis acids having vacant orbital, which is able to consume the electron or accept the electron from chlorine and form electrophile. Okay, and in the formation of electrophile in this process like CH3Ca react with FeCl3, but this has vacant orbital, this chlorine donates electron, formation of FeCl4 minus plus CH3 plus. This is the electrophile. Okay. This electrophile reacts with phenol to form one ortho substituted or orthomethyl phenol and one paramethyl phenol. Okay. Let us see the mechanism. First of all, there is formation of electrophile LCl3 react with CH3Cl. This chlorine transfers its one pair of electron to aluminum, and there is formation of LCl4 minus plus CH3 plus. If there is ortho attack, there is formation of orthomethyl phenol, and if there is para attack, like this, the one pair of electron transfers here, this transfers here, and this one attacks here. There is formation of intermediate like this. and to develop hydrogen there is aromatization and formation of paramethyl phenol. Okay, so this is Frederick-Taub alkylation. So similar to this Frederick-Taub alkylation, there is also one more reaction called Frederick-Taub acylation, in which phenol reacts with, instead of alkyl chloride or alkyl halide, phenol reacts with acyl halide. Let us consider acyl chloride like CH3 COCl in presence of anhydrous AlCl3 to produce ortho-substituted product and para-substituted product. Okay, so the reaction is almost similar, but here the electrophile is different. So the generation of electrophile takes place as CH3C double bond Cl react with nitrous AlCl3. This is the kind of orbital, so this chlorine donates electron and there is formation of CH3C double bond of plus. This acts as an electrophile. So now the phenol reacts with this electrophile and there is formation of ortho-substituted and para-substituted phenol. Okay. Next to this field called alkylation and acylation, there is mercuration, in which the reagent that is reacted, phenol reacts with mercuric acetate such as HgOCO CH3O2. This reacts and formation of ortho-substituted HgOCO CH3 and with that formation of CH3COOH. The mechanism of this reaction proceeds as this is phenol react with mercuric acetate like HgOCO CH3 single bond O CO CH3. Now the double bond electron attracts Hg and this removes as CH3CO minus and there is formation of mercury compound. And if you see in aromatization, there is removal of H plus. That H plus is conjugated by CH3CO minus to form CH3COOH acetic acid. Okay, this is mercuration of phenol. Okay. Next, there is one special name reaction that is known as Kolbes reaction. Okay. If you see Kolbes reaction, sodium phenoxide reacts with carbon dioxide and proceeded by reaction with mild acid to produce salicylic acid. Okay, if you see this reaction is known as Kolbes reaction. This Kolbes reaction, the reaction is starting material is ONA, that is sodium phenoxide, reacts with carbon dioxide to produce ONA phenol OH, then CO minus Na. For the reaction with HCl, it produces salicylic acid. Okay. So the reaction mechanism for this reaction is this sodium phenoxide is obtained from phenol. Okay, if we consider the reaction from phenol, then phenol is treated with NaOH. It produces, but treated with sodium, it produces sodium phenoxide, ONA. Then reaction with carbon dioxide structure is C double bond O. Okay. If you see this ONA is O minus and Na plus. Now this O minus negative electron transfers here. This attacks to carbon and transfer of electron from carbon to oxygen. So this forms double bond O, then H, then C double bond O minus. If there is O minus, beside this there will be Na plus. Okay. In the next step, removal of H, O minus. This O minus will consume H plus, and there will be formation of OH, COO minus Na plus. This further will react with dilute HCl to produce salicylic acid. Okay. This reaction is known as Kolbes reaction. Okay. Next one named reaction that is known as Remer-Tammann reaction. In this reaction, starting from phenol reacts with CHCl3 chloroform in presence of sodium hydroxide to produce here sodium phenoxide plus CHCl2, and for the reaction with NaOH, it produces, there will be nucleophilic substitution reaction and two OH groups will be attached. So this is unstable, so the water will be released or there will be dehydration and formation of salicylaldehyde and further hydrolysis will produce salicylaldehyde. So now we'll see the mechanism of this reaction. So first this chloroform will react with sodium hydroxide like CHCl3. This will react with sodium hydroxide. This sodium hydroxide will break down and produce Na plus OH minus. This OH minus as a base will remove the acidic proton and this will produce CCl3 minus, and this CCl3 minus will produce CCl2 radical and Cl minus ion. Okay. So now the reaction will start from CCl2 radical. First this phenol will react with CCl2 radical to produce OH plus, then CCl2 minus. So now this will undergo aromatization and there will be formation of CCl2 minus. The CCl2 minus will consume that H. Okay. Consume that H and this will become CH, Cl2, and here this will be OH. Okay, as this is OH and reacts with aqueous medium in presence of sodium hydroxide, NaOH, this will produce ONA and CH, Cl2. Now this will further undergo 2NaOH. NaOH will produce OH minus ions which will act as a nucleophile and this will substitute these two alkyl groups. So hence there will be formation of CH, OH and ONA. So this will undergo dehydration, the formation of sodium hydroxide into ortho position, sodium peroxide. The ortho position there will be aldehyde group or CH group. Then this will undergo reaction with mild acid to acquire the H plus ion. There will be formation of salicylaldehyde. Okay. This is known as Raymond-Tamon reaction. You see, okay, means the name Raymond-Tamon reaction. Okay. RIEMERTIEMAN, Raymond-Tamon reaction. So including this or excluding this, if this react instead of chloroform, this react with CCl4 carbon tetrachloride instead of salicylaldehyde. This is salicylaldehyde. This will produce salicylic acid. If you see the reaction and the mechanism, the reaction will be phenol react with CCl4 to produce up to NaOH and further hydrolysis. This will produce COOH or salicylic acid. Okay, the reaction mechanism for this reaction will be the reaction mechanism okay, let us see the mechanism. If instead of CHCl3, if we react this with CCl4, if we react this with CCl4, so first of all on reaction of CCl4 this will produce OH and CCl3, this and further reaction with 3NaOH, this will produce 1 OH group and to 1 carbon, 3 OH groups will be attached. These two OH groups will undergo dehydration, there will be minus of H2O and formation of here phenol C double bond O OH. Okay. Formation of salicylic acid. Next reaction is diazonium coupling. This phenol undergoes reaction with benzene diazonium chloride to give diazonium coupling. Okay, if you see the reaction benzene diazonium chloride, N2 plus Cl minus reaction with phenol to produce in presence of a base to produce azo compound, which is orange dye. Okay. The reaction mechanism of this reaction will be, first of all, the base will react with phenol. There is hydrogen, this is the acidic hydrogen, so first of all this base will consume a D protonate and there will be formation of carbanium. Okay, negative charge here. Then this benzene diazenyl chloride, the structure for benzene diazenyl chloride, that is N triple bond N plus, this will delocalize and formation of the resonating structure will be N double bond N plus. Okay. So now this negative charge will contact to this and there will be formation of this coupled product. Okay, this reaction is known as coupling reaction with benzene diazenyl chloride. Forgot to mention the name. This is known as coupling reaction. Okay, next reaction we will see Claisen rearrangement. So with this Claisen rearrangement we will finish this topic of phenol. Okay. In Claisen rearrangement, the crotyl phenyl ether, this rearranges to produce orthomethyl allyl phenol. Okay. This is the rearrangement reaction in which crotyl phenyl ether, that means O CH2 single bond CH double bond CH CH3. This is called crotyl phenyl ether, right? Crotyl phenyl ether. So this undergo rearrangement to produce phenol in ortho position. There is formation of allylic compound. This is known as orthomethyl anyl phenol. Orthomethyl allyl phenol. Okay. So this reaction takes place by the help of heat. Okay. The mechanism of the reaction will be, let us consider oxygen and this is CH2 single bond CH double bond CH2. Okay, in the next step this double bond will attack this carbon, double bond will transfer here and this will be O minus. Okay, this will be O minus double bond O to this. There is one hydrogen already attached and CH2 single bond CH double bond CH2. Okay. Now the double bonds are here. This will undergo aromatization and then formation of phenol OH and to this sorry, here one, also one CH3 group is also attached. This will form, okay, to this one CH3 group is also attached, so there will be formation of CH, CH3, CH double bond, CH2. So this is orthomethyl allyl phenol. Okay. So this Claisen rearrangement reaction, we finish up the phenol topic. Next we will move to ethanol. So if you have any doubt regarding this, let me know in the comment section.